Okay, so this is our first introduction to partial differential equations, and we're going to look at some of the classic spatial partial differential equations. We're just going to look at them in two dimensions. So in x and y, we have the Laplace equation, which is the Laplacian of phi equals 0. We have the Helmholtz equation, which is the Laplacian of phi plus some constant, k squared times phi equals 0. And then we have the Poisson equation, which is again the Laplacian of phi, but the Laplacian of phi equals some density function. And we're going to think about doing this in a rectangular domain. And in that rectangular domain, we're going to have the directions x and y, and we can have the extent in y and the extent in x, 0, 0. And so we're going to be thinking of solving this inside that rectangular domain, and we're going to need conditions about phi or its derivatives along the boundary that bounds this domain. How do we know that? Well, every time we have a differential equation, we need either an initial condition or a boundary condition to set the specific parameters. In this set, it's a second order differential equation, so we need 2, and we need 2 in each direction. So we have 2 in x, 2 in y. That's the way it's going to work for this one. If I had made another shape here, it still would have had 2, however you sliced it, on that interior domain, and that would have been fine too. We're going to use this form because it makes our life a little bit simpler later when we end up with sines and cosines or sinches and coshs instead of other special functions. Okay, so how do we solve these kinds of equations? Two parts. We need a particular solution if we have a density function like this in the Poisson equation. The particular solution will just be something that when I differentiate twice gives me that same density function back. So if this density function was something simple, like a point source, you could probably figure out a phi that would give you something when you took the second derivative that would only have a second derivative at one location, something like peak. If you had a linear function in x or a linear function in y, you could build a polynomial for phi that would, when you differentiate it twice using the Laplacian, which remember in this case the Laplacian squared is going to be the second derivative with respect to x plus the second derivative with respect to y. That's what it means, and so it's going to be second derivative with respect to x, second derivative with respect to y, acting on this phi function, and that would give us the density. So if this was, say, x, then I could use something like 1/6 x cubed as a particular solution for phi, and so I break phi down into a homogeneous part plus a particular solution part, and the particular solution part just cancels this right-hand side. Once I'm done with that, I'm going to have to still find the homogeneous solution, which is going to have unknown constants in it, and those unknown constants will allow us to satisfy the boundary conditions, which are really only applied on the total phi, not on the particular phi. So here's the process. If I have an inhomogeneous solution, I find a particular solution to balance it, and then I go back and find a homogeneous solution, which is the solution of the Laplace equation, which is the same as the Poisson equation with no density function on the right-hand side, and then I would end up with a total solution that would be constrained by the boundary conditions to remove all of the remaining lingering constants. You might wonder why I was kind of casual about how we do that with the particular function. It's because there's actually more than one way you can find a particular function to balance this density source on the other side of the Poisson equation. It doesn't matter what you get, because if you do something funny, matching the homogeneous solution to the boundary conditions will undo whatever you've done. So these equations are all unique with adequate boundary conditions for phi, but the homogeneous and particular solutions are not. The non-unique parts will cancel out. Okay, so as we hinted at, the Helmholtz equation and the Laplace equation are homogeneous equations, and we actually know a lot about homogeneous equations because we know how to solve them, homogeneous ODEs, by just plug and chug with an exponential form. We're going to do exactly that same thing, but let's do it on the Laplace equation after we do something that's called the separation of variables first. So suppose we assume that phi is actually composed of the product of two different functions, one that depends only on y and one that depends only on x. It's not clear why I would be doing this right now, but it's clear that some solutions might look like that, and also because all of these field equations are linear in phi. If we found one solution that looked like this, or multiple solutions that looked like this, we could add them together and build still more solutions. So if there's a whole class of solutions that have this form, I could add them together over many different versions of it in order to help satisfy my boundary conditions. Okay, off we go. Plug that into the Laplace's equation. I take the second derivative of the x function times y plus x times the second derivative of the y function. And when I'm taking the x derivative, I don't have to mess with taking the derivative of the y because it doesn't depend on x. And when I'm taking the derivative of the y, I don't have to mess with taking the derivative of the x because it doesn't depend on y. Okay, so that's supposed to be equal to 0. That's my Laplace equation. I can divide through. So since these are homogeneous, they're all satisfied if phi equals 0. But that's a trivial solution, and it probably doesn't match the boundary conditions. What I'd like to do instead is I'd like to divide through by x times y, which is just this particular phi. And I can assume it's not 0 in most places, at least, because it's not the trivial solution where phi equals 0. So I'm going to divide this whole equation on both sides by x times y, and I'm going to collect the x part on this side, x double prime over x, equals minus y double prime over y on the other side. Okay, so this is the key step in the separation of variables argument. This side only depends on x. This side only depends on y. If this side were actually to depend on x, that is, after I take the derivative of this function and divide it by itself, then this side would be a function of x, and I could choose any x I like. Same over here. If this were actually a function of y, then I could choose any y I like and make this vary along with however it varies in y. But since those have to be equal to each other, I actually don't have the freedom to do that. They must both be constant. This can't actually depend on x because if it did, I could do something with x that I couldn't match by choosing y because y and x are independent of each other. Similar to this side, can't really depend on y because I could do something that had a function in y that I couldn't match with any particular value of x. So I can set both of these equal to some constant, and let's call it k squared. And I can set it equal to k squared on both sides, because whatever. Now look at this. That's not a PDE anymore. And look at this. That's not a PDE anymore. We've got two ODEs that are now uncoupled from one another with these separation constants k squared. Okay, and we know how to solve this because this is just a homogeneous ODE. So I could come up with x equals a e to the mx plus a minus e to the minus mx. And why am I putting m's in there? Well, I was just testing it, but if we plug this in there, we take the second derivative, we get an we get an m squared out in this term, we plug this one in, we get a minus m, and a minus m, that's also an m squared, and then we divide through by the function itself, that cancels out the exponential and the coefficients, but it leaves us with an overall m squared there. So I actually don't even need to put it as m, I can put it as k directly. Cool. And you might say, why did I choose k squared? Was because I wanted right there to have it be k. And you might say, actually, I didn't know that k squared was going to be positive because I just came up with some constant. I just said it was going to be a constant. It could have been any constant. What if it was negative? Well, then I would have had an ikx and an I minus ikx, and this would have been an oscillating function. Well, let's jump over to the other side of the equation and say, well, whatever we chose over here, suppose this one is exponentials, then this side for the y function is the same game, except we've got one minus sign here. So we get y equals b plus e to the plus iky plus b minus e to the minus iky. So if this one is exponential, this one is oscillatory. Other way around, if this one is oscillatory, this one is exponential. We put these two together and we see we've got something that looks like kx, iky. It looks like cosh or sinh, Maybe, depending on what the values of these a's are. This one looks like sines and cosines. Well, let's think about how we would determine these coefficients based on the boundary conditions. We've already eliminated k, we don't need that, but we do need to still find these boundary conditions. So I could just evaluate all the way along here at y equals 0, which means that this goes to 1 and this goes to 1. And so my product of the two, x times y, which is my phi guess, would be just equal to a plus e to the kx plus a minus e to the minus kx times b plus b minus. Okay, that doesn't look like much, but let's continue and look at this side. If we go up this axis, we get the same thing, except we have evaluated x equals 0, and the other side would have been non-zero. So we would have gotten a plus a minus times b plus, e to the I k y plus b minus e to the minus I k y. All right, this is looking kind of promising, because this is actually something that looks a little bit like a term in a Fourier series. And now remember back to what I said in the beginning, because this is a linear function, I can add together as many of these are convenient. So we could actually make our total solution phi a sum over lots and lots of a's and b's, each which links up to a k. So I have this one is the one for a particular k, this one is the one for a particular k, one for a particular k, and I sum them over all the possible values of k I could find, and what I find is that this term, when I go to evaluate this boundary condition, is actually giving me the Fourier transform of whatever function I choose to set for my boundary condition on phi. In the other direction, I would be exponentially decaying with the same k, so I decay, here's my wave number, that's the rate at which this goes up and down over here on this side as I increase in y, but on this side I would set the rate of decay into the interior or the rate of growth into the interior. If I go all the way around and I keep switching which one of those is the Fourier transform and which one of those is the exponential, because remember, I got to choose whether k was the negative form or the positive. I got to choose whether k squared was a negative or a positive. I could do a Fourier transform in y, another Fourier transform in y, Fourier transform in x, a Fourier transform in x, and I could match all four of those boundary conditions with 4 different Fourier transforms. And along with each Fourier transform, I would have an exponential growing or decaying solution that allowed me to patch through the middle from one side to the other. And moreover, one more thing to think is that would actually be a smooth function, because we know actually that the Laplacian itself it highlights anomalies. If you have a second derivative that's positive or negative because you have a localized anomaly, then you get a Laplacian, an anomaly in Laplacian centered about that positive or negative anomaly from its neighbors. And so to say that we're solving Laplace's equation means that we have something that doesn't have any localized anomalies. It's actually if you took a sheet of rubber and just deformed it on the outside and it was stretched in the middle, it wouldn't have any bumps in the middle, it would just kind of uniformly stretch. That's the kind of solution we are imagining would happen here. That's the kind of solution that comes out of a Laplace's equation because it has no localized anomalies in the interior, but it's free through this Fourier transform version to match to any function you like all the way along the boundaries, and then it smoothly connects through the interior. Great. Let me pause for a second. I'll come back and we'll talk about the Helmholtz, which is closely related. Okay, let's suppose that we do the same separation of variables that we do in the Helmholtz equation. What we're going to find is we would have the second derivative with respect to x of the x part plus y, second derivative with respect to y of the y part, and then we'd have just the same there. So let's write it out. X double prime y plus x y double prime. That's the Laplacian plus k squared. And this is a different k than the k we just used as a separation constant. This is the one that comes from the original equation. So actually, let's call it something else. Let's call it alpha squared. Now let's call it b squared. B squared times xy equals 0. Now I divide through by x times y, and I get x double prime over x plus y double prime over y plus b squared. Okay? We have exactly the same situation here. This term doesn't depend on y. This term doesn't depend on x. So this can't actually be a function of x and still balance something that's a function of y. This is just a constant, so it doesn't do it much. Now if we jump ahead to our exponential guess and check for something like this, where we have this equals a constant, or this equals a constant as our ODEs, then we would know that we would just get whatever the exponent here is, the exponent factor, whether it's a plus m or minus m, let's just take it's m, and then for this one we get a plus n or minus n, and then we'd have b squared equals 0. So we would have a solution that looks an awful lot like the solution to the Laplace equation, and then we'd have an e to the m x a plus a minus e to the minus mx multiplied by b plus e to the ny plus b minus e to the minus ny. And now we really don't know much about whether these are complex or real, but we do know that they'll always satisfy this equation. So if b squared went all the way to 0, then we'd recover our Laplace equation solution, and we'd have just m being real in one case and then imaginary in the other, so that they would cancel out, and m and n would have the same magnitude, but one would be real and one would be imaginary. Or if they were not that way, when we had b being a positive number, then you can have both of these being imaginary and this being the balance point for it, so I could oscillate in both directions, or I could oscillate in one direction, kind of extra, and then I would have two positive numbers to balance, so it would be decaying at a different rate, at a rate that depended not only on the oscillation frequency, but also on this b factor. So that's the solution to the Helmholtz equation. So we've solved the Poisson equation, the Helmholtz equation, and the Laplace equation through the series of finding first a particular solution to satisfy the right-hand side of the Poisson equation, and then looking for the homogeneous solution, which is the Laplace equation, the Helmholtz equation, using separation of variables, and it tends to have an exponential times an oscillatory part, or in the Helmholtz equation it could be two oscillatory parts, but they balance together through this equation on the components of the exponent. All right, great.